Hello and Assalamu alaikum. My name is Mr. Haider Ali Beg, and today the topic of my presentation is logic gates. So, let me go over what we're going to cover in this presentation. The first thing that we're going to cover is logic gates, then representation of logic gates, AND gate, OR gate, NOT or inverted gate, NAND gate, NOR gate, XOR or exclusive gate, and then we are going to conclude our presentation. So let us move on towards our presentation. Okay, so the first question is that what are logic gates? A logic gate is an idealized or physical electronic device implementing a Boolean function or a logical operation performed on one or more binary inputs that produces a single binary output. Examples of logic gates are AND, OR, NOT, XOR, XNOR, NOR, etc. Logic gates can be described by several symbols including mil, slash, NC, IEC, and DIN symbols. The next thing that we're going to cover are the representation of these logic gates. Some logic gate representations are shown above, which are the DIN, mil, and IEC symbols. At the leftmost side, you can see the DIN symbols. In the middle, you have the mil symbols, and to our right, we have our IEC symbols. But the one that we occasionally and normally use in our course are the mil symbols, while also sometimes utilizing the IEC symbols. Now let us move on towards the actual gates. And the first gate that we're going to discuss is the AND gate. The AND gate is a basic digital logic gate that gives a high output result only if all the inputs to the AND gate are high. The AND gate is used for logical conjunction. The general expression of an AND gate is x is equals to A dot B or AB combined. We can say that the AND gate is somewhat similar to basic multiplication in simple algebra. AND gates are available in IC packages. The 7408 IC is a well-known quad 2 input AND gate. If we are to look towards the image, we can see the basic representation of the AND gate. And, and to the bottom, we can also see the truth table of an AND gate. But if we are to look closely, we can see that the output of an AND gate will remain low or zero only if one of the inputs of the AND gate is low. It will be high or one if both the inputs are high. Now let us move on to the second gate, which is OR gate. The OR gate is a basic digital logic gate that gives a high output if one or all the inputs to the OR gate are high. An OR gate is used for logical disconjunction. The general expression for an OR gate is x is equals to A plus B, and we can say that it is similar to addition in simple algebra. OR gates are available in IC packages. The 4031 IC is a well-known 4-independent 2-input OR gate. If we are to look at the image, we can see the basic representation of an OR gate, and to the bottom we have the truth table of an OR gate. By observing the truth table, we can see that its output will always be high even if one of the inputs is high, and will only be low if both the inputs are low. Now moving on, we've got the NOT gate. Now NOT gate is the most fundamental gate of all the logic gates. The NOT gate is a basic digital logic gate which changes the state of the bit. A NOT gate is also known as an inverter. It is used for logical negation. The general expression for a NOT gate is x is equals to A bar. A NOT gate is embedded into a NAND or NOR IC, among others. If we are to look to the image, we can see the basic representation of a NOT gate. And if we are to look at the truth table, we can see that it just basically changes the state of a bit. If a bit is low, then after passing through the NOT gate, its state changes to 1. If a bit is 1, then after passing through the NOT gate, its state changes to 0. The next gate that we are going to discuss is the NAND gate. The NAND gate is, in simpler words, just a NOT gate attached to an AND gate. The bubble on the NAND gate indicates the NOT. A NAND gate is a logic gate which produces an output which is low only if all its inputs are high. It is basically the complement of an AND gate. The general expression for a NAND gate is X is equals to AB bar. A NAND gate is also known as a universal gate as it can form all the basic logic gates. Now, I could not touch upon the aspect of the universal gate much more because this topic is given to another classmate of mine. A NAND gate can be used by the 4011 IC, which implements four independent two-input NANDs. If we are to look towards the image, we can see the basic representation of a NAND gate. And if we are to observe the truth table, we can see that it is exactly the inverse of the AND gate. It will display high outputs only if there is a single low input, and it will only show a low output if both of the inputs are high. The next gate is the NOR gate. The NOR gate is, in simpler words, just a NOT gate attached to a OR gate. If we are to look at the figure, we can see that the bubble indicates the NOT gate. A NOR gate is a logic gate which produces an output which is high only if all its inputs are low. It is basically the complement of an OR gate. The general expression for a NOR gate is X is equals to A plus B bar. A NOR gate is also known as a universal gate as it can form all the basic logic gates like the NAND gate. A NOR gate can be used by the 4001 IC, which implements four independent two-input NORs. If we are to look at the image, we can see the basic representation of a NOR gate and its truth table. By observing the truth table, we can see that its output will always be low even if one of the inputs is high, and its output will be high only if and only if both of its inputs are low. So the next gate that we are going to discuss is the XOR gate or exclusive OR gate. The XOR gate is a digital logic gate that gives a high output when the number of high inputs is odd. An inverted XOR is known as an XNOR. It is also known as an exclusive gate in addition to XNOR. The algebraic expression for a XOR is X is equals to A dot B bar plus A bar dot B, or X is equals to A plus B dot A bar plus B bar. The logic symbol used for a XOR gate is a little bit special as it is a plus sign enclosed inside a circle. If we are to look at the image, we can see the basic representation of a XOR gate. And if we are to observe the truth table, we can see that the outputs will only be high if there are a number of odd high inputs present. Otherwise, the output will always be low. Now, to conclude my presentation, I am going to show you an example circuit which is made by the combination of several logic gates using wires to connect the logic gates. Over here, we have an expression A dot B plus C bar dot D inverse. And to make this circuit, we just basically join the basic logic gates with wires to get the desired output. So this was the basic overview that I could give you of logic gates, and I thank you all for listening.